Good afternoon, everyone, and thank you, Causal AI, for having me. So, today, I'd like to talk about the maintainers, people whose job is to keep things working, put simply. And given that I'm in the business of railway transportation, the kind of maintainers I have in mind are the railway staff that make sure the trains operate reliably and safely, day after day, because this is important. On the one hand, we want trains to be reliable because we all commute and need to make it to the office on time. On the other hand, we want them to be safe for obvious reasons. Safety is of utmost importance in railways for the passengers, for the employees, and for the public in general. Safety is a priority that must become before all others, and the risks must be minimized. So, in our causal inference context, what could be the effect of exposure to danger due to an unreliable or unsafe train? And you're probably thinking about accidents, right? So, this is Paris, 1985. The historically famous derailment on the Montparnasse station. So this particular steam engine had an issue with the air brake system that was available at the time, and as a result of this accident, there was one casualty and a partial destruction of the infrastructure. But the railway community learned from this catastrophic event, which spurred the development of more effective braking systems. So fast forward 70 years. Modern trains, such as the ones we use today, equip what is known as a blended braking system, where two different braking technologies are smartly integrated. So on the left-hand side of the slide, you see friction brake. In this setting, compressed air pushes the plunge of a piston, which moves the caliper, which squeezes the brake pads against the brake disc. And friction eventually transforms the kinetic energy of the train into heat. On the right-hand side of the slide, you see a schematic of a dynamic brake. In this setting, the traction motor is used as a generator. So the train in movement keeps spinning the rotor. The electrical resistance induces currents in the windings, which are then routed back to the grid for their reuse and into the rheostat, which dissipates the remaining energy as heat through the Joule effect. And this is all a bit of a mouthful, I know, but this braking technology is definitely more effective than the technology the steam engine had. So, here comes the question. Would the former steam engine have stopped in time had it equipped one of these blended braking systems? We can probably guess the answer to this counterfactual question. There's some missing information, that's true, but it's an interesting question nonetheless. The trade-off with this increase in effectiveness is an increase in the sophistication and complexity of the systems, which in turn make the job of maintainers increasingly more difficult. So in the middle picture, you see a brake control panel that's full of stuff. You need to know what you're looking for when troubleshooting one of these systems. And this is only half the story, so I'm excluding the traction unit. So, is this increase in effectiveness and complexity worth it? We're going to assume that it is, because nowadays, we also have data. And with data come predictive systems that observe international standards, such as this one shown here, which provide guidelines to collect the data, process it, and provide the results in a way that the maintainers can make use of them in order to do their job more effectively. And with all these, we engineers can then come in and develop predictive maintenance solutions, which have to accomplish three main goals: the detection of anomalous behaviors, the diagnosis of the root causes, and the prognosis, which is the estimation of the remaining useful life, which is the time or the mileage left before the failure appears. So, does it make sense what I'm saying? The question now is data all we need to provide answers to these or to accomplish these three objectives? Nowadays, we have data collectors of all sorts. We have the GPS, we have the Internet of Things, we have powerful computers able to generate reams and reams of data. And trains are better today than they used to be in the past. But the world is changing constantly. And in this changing setting, it is reasonable to have some doubts. Will the extant technology perform well in this changing environment? Will that new technology developed in the lab perform well once we deploy it in the real world? And again, is data all we need to provide accurate, unbiased answers to these questions? I have some qualms about this, but it turns out that predictive technology is kind of limited in this sense. And we also have the causal technology, right? And causal inference is precisely the science that allows us to intervene in the world, change it, and evaluate the impact of these changes. So we're probably on the good track if we adopt causality in this predictive environment. So, predictive causality, causal prediction. Doesn't make sense to have these two concepts on the same page, because causal systems are not predictive systems. There's a fundamental difference regarding the way that they manage the dependencies among the variables that we use to model the world. Predictive systems are focused on mapping independent inputs to outputs, and will do whatever it takes to adjust their set of parameters in order to minimize a classification or regression loss, oftentimes rendering them uninterpretable, which penalizes the confidence that we can give with the solutions that we develop. Alternatively, causal systems are focused on modeling these variable interactions, making it clear what's going on under the hood, and also possibly helping us deliver solutions with a greater degree of confidence. So, does it make sense to adopt causality in this predictive environment? My contention is that it makes perfect sense. And in this talk, I will try to build a convincing case for doing so. And to this end, I will borrow the well-known Simpson's paradox example, but instead of relating exercise to cholesterol, I'm going to put maintenance in the abscissa and cost in the ordinate. But the message that the graph conveys is exactly the same. Well, it may seem that the more maintenance you do, the more money you will spend. This is a deception introduced by the confounding effect of the age on your fleet. So, there may be different approaches to conduct the maintenance of the assets. And in fact, we have names for these. The kind of approaches that only fix the things that break are called corrective, and they're shown in red at the top. They are the ones that eventually spend the most. And then there are the schedule approaches shown in yellow. These approaches build maintenance plans at the beginning of a project based on some historical averages of degradation. And these are okay. They can reduce some of the cost, but up to a point, due to the overly conservative and risk-averse criteria of railway operation. And then there are the predictive approaches, shown in green. These approaches use sensors to collect data from the field, and they estimate the actual degradation conditions of the assets. And then they use this information to drive the maintenance actions in a more dynamic way. So these are the kind of approaches that enable us to explore new business cases that comprise the observation of unexpected issues, and that also allow us to exploit the full life of the components. Obviously, this is where we want to be with data science and causality. And in fact, the gist of these things I'm talking about is pretty well known to the maintainers, because engineers have been using them for ages under the guise of the failure mode, the mechanism, and the effect analysis, which is a set of documentation that describes the problems from the incipient point of failure until the system crash. And if we read these through the lens of causality, we are going to find the same fundamental underlying concepts, because we can liken failure mode to root causes, mechanisms to mediators, and effects to outcomes, therefore building a beautiful causal graph that we can exploit with the tools of inference. So up to this point, I would say that we're in a pretty good position to justify the adoption of causality in a predictive environment. And to further convince you of this, I'm going to share with you two specific use cases that we developed at Alstom, where we leveraged that causal technology in a context of language and in a context of subsystem events, which are the kind of messages that flow in the backbone of the trains. So, to the first use case, the one that involves natural language or technical language, as this term better reflects the engineering lexicon and semantics of the return on experience records that we use for this research. So return on experience is a database, a written database, that describes the problems as they are found on the shop floor, and after the investigations, they also contain the information, they also describe their root causes and the solutions that were introduced to solve them. So it's interesting information for us to mine in order to provide further knowledge, this added value knowledge for the maintainers. So, while traditional NLP approaches would have tackled this setting using the localist representations with sparse vector spaces, we have here adopted a more modern approach using deep learning, so things like ChatGPT, that kind of stuff. So in this case, we're building distributed representations with dense vector spaces that already embed the causal information that we're interested in analyzing. So the point of this research is to develop causal word embeddings as a fundamental building block for other downstream tasks, such as root cause analysis. But obviously, these word embeddings are not like the traditional ones where you learn the local context of individual words. So these words for natural language, because that is governed by a context-dependent grammar. In this case, the causal information is found in the entailment of whole text. So our specific proposal for doing root cause analysis troubleshooting is to treat the whole text as a bag of words, model their entailment in the diagnosis direction, while conditioning on the context of the project to adjust for any confounding, which is what makes sense given the causal graph that describes the entailment in the text, which is shown up there at the top right-hand corner of the slide. So on the left, you see the neural encoding architecture that we use for learning this. We know from NLP research literature that we can peek into this learned representation by extracting the principal components of the embedding. That's what we're showing in the middle picture. And then by using a similarity metric, such as the cosine distance, we can then align the problem to their potential root causes and provide these one first step of added value knowledge for the maintainers. And finally, for verification purposes, we also conducted some sort of alignment analysis by taking into account the average probabilities from the model, taking also into account the fault tree that we derived from the FMEA documentation that I described previously. In this case, it turns out that if we get the wording that was used to describe the direct diagnosis and we compare it with the others, we found an overlap over 70%, which signals that what we are learning is meaningful and therefore it is valuable for the maintainer. So that was the first use case. The second one, the one that involves the subsystem events, which we here treat as binary variables that evolve in time. In this case, the goal of the research is to develop two modules, the one that detects the anomalies and the one that troubleshoots their root causes. And the interesting bit of this research, the capstone of the project, is the use of the variational autoencoder for implementing both modules. So autoencoders are probably the go-to solution for engineers dealing with an unsupervised environment, such as this one, where we only have data that comes from commercial surveys. And then this autoencoder model learns the pattern of normal behavior and then uses the reconstruction error to signal the presence of an anomaly. In this case, what makes the variational type of autoencoder especially interesting is the added regularity in the embedding, which then becomes a manifold, which is a locally Euclidean space. And then we can use it for generative purposes, which we exploit for doing interpolations and extrapolations, which is especially interesting in an environment where we don't have examples of failures. So on the left, you see the neural autoencoder architecture with a focus on the bottleneck, which is where the manifold is to be found. And in the middle picture, you see a representation of this manifold, where you can see how the normal data gets clustered at the center. Then, on this space, we can fit a smooth probabilistic function to signal the risk of an anomaly. And once we introduce a threshold to that function, we tessellate the space so that anything that falls out of this corral is logically regarded to be an anomaly. And obviously, once we spot an instance that is suspicious to contain an anomaly, we then route it into the root cause analysis module. And the development of this module turns out that variational autoencoders can also learn causal structure in the data, provided that we give them causal cues along with the variables, and we also introduce some masking layers to implement these variable dependencies. In our case, we didn't have these kind of examples. It was a purely exploratory endeavor, but we could still make use of the algorithms from the area of causal discovery to have an idea of the causal structure that was likely to be learned in our environment. And this is what we show there on the right. Those are the 10 most frequent events in our environment, 5 of which belong to the traction system, 5 of which, so the remaining 5 belong to the brake system. That's again the blended braking system. And the orientation of the arrows is what already gives us some useful information. And what we read on the diagram is that the cause-effect relationship that is established for these events occurs from the brake system to the traction system. So root causes in the traction are to be found in the brake, at least for these most frequent events. Obviously, if we had taken different variables, the results could have changed, and also if we challenged the set of assumptions that we took for building that we might get some different results. In this case, we had a multivariate setting, so we solved that with conditional independence tests. That is a Markov equivalence class. We also discretized the time and evaluated the impact of different time lags, but what we got, at least, is meaningful from an engineering perspective and is therefore valuable information to provide to the customers. And before I bring my talk to a close, I would like to highlight some challenges and opportunities as key takeaways. Regarding the challenges, I like to say that the knowledge in the field of causality is very fragmented, and this is a problem, creates a lot of confusion. In terms of inference, we have the potential outcomes framework, we have the DAG framework. Scientists that are proponents of one approach don't want to hear what scientists that are proponents of the other approach have to say. This is all a bit of a mess. And then we have the discovery part, which seems to be a world completely apart. And I feel that given that discovery has its origin in philosophy, such statisticians don't want to hear about that. They despise those kind of algorithms. And truth be told, engineers that are concerned with getting things done and delivering something useful can really benefit from this kind of algorithms, because the experts that could provide all this knowledge about the relationships among the variables can't simply make the time to sit at the table and go through all this. So this is a kind of a good solution to get the problem solved. And regarding the generalizability of the solution, that's also one of our challenges, because the kind of products that we build eventually get deployed all over the world. So the assets get subject to different stress conditions. So if we're able to extrapolate and transport the outcomes from one setting to the other, that is advantageous for us. And also, solutions might be developed in one end of the world, but the production is typically delocalized, close to the geographical area where the asset is to be used, which eventually introduces some dependencies with the local suppliers that also end up changing that original design. So at the end of the day, we end up with many different models that are similar but not exactly the same. So we have to be careful when drawing any extrapolations. And regarding the opportunities, I'd like to say that causal inference is a very dynamic field in full blossom within the AI community, which is great for attracting talent in data science. It has a great capacity to adapt to change, which makes perfect sense in the evolutionary nature of the world. And the return of its investment is driven by many different factors. I will briefly mention financial factors. We reviewed some of the typical business cases for predictive maintenance. And then there are safety factors, obviously, and there may be many others. So, to me, causality is kind of a great science to adopt today. And I am sure that it will help us build a better tomorrow. And at some point in the talk, I said I would try to build a convincing case for using causality in a predictive environment despite of this contradictory meaning, but did I do a good job to convince you? Thank you.
Great. Thank you very much for that talk. And I think that next to last slide that you were showing is something that's just universally applicable. I think we could all poach that slide and use it for all of our presentations in the future. So really, really thank you for all of that. Are there any questions?
Thank you.
We have one right here in the middle.
Thanks for the talk. The first use case you had, that was the embeddings use case. You're ingesting...
That one? Language
Yes.
one?
Yeah. So here it ingested problem reports and created these word embeddings that are like points of failure to get to the root cause, or can you speak more to this use case a little bit?
Yeah, in this case, the return experience records contain both the root causes and the solutions, but we here focus the attention on the root causes. So we learn them by drawing that association from the problems to the root cause. That is the diagnosis direction in the model. But we also introduce the local context of the project to adjust for any confounding, because that is the way the data was given to us. So we know that the association, the entailment of the text has that causal structure, so we obviously had to take that into account in order not to get biased embeddings or things like that. Yeah. So this is what kind of work in progress. These are some of the initial steps in this domain, but I think it already gives us promising results. So we'll continue to work on these, and you're probably going to see more about this in the near future. Yeah. Thank you for your question.
Okay, so I think your use cases are super powerful. The second one.
Second one.
No? So in this one, my question is more on interpretability, right? You're trying to get to...
And what? Please repeat.
Interpretability.
Interpretability, okay.
So did you lose that? Did you lose interpretability in this approach?
Well, in this case, we can have two levels of interpretability, and we wanted to highlight the limitations of doing a straightforward sensitivity analysis. When you take the autoencoder and you just activate some of the inputs and see the impact on the outputs. But this is mainly driven by correlations. So we wanted to compare that with the kind of information that the causal diagram provides, because that is evident, which variable relates to what. Obviously, we have to accept the limitations of the techniques, but to me it's okay. I mean, that is not perfect. I think we've discussed this topic many times during the conference. We don't need the solutions to be perfect. We need to get the customers from the position they are today to a better position tomorrow. So as soon as we have something to add value to their business, we can ship what we have.
Thanks.
Yeah.
So again, on this use case, you mentioned that you investigate the structure of the latent space to perform some causal discovery. So the question is, do you perform this causal discovery on the latent space or on the feature space, or I mean on the variables, on the observed variables? And if you do it in the observed variables, what kind of mapping do you have to translate some structure in the latent space to the observed space?
Well, the learning occurred in the data space. So when I think what you mean the feature space, to me the feature space is the manifold, because that is where the learned thing is. But we did that in the data. In the end, it's an autoencoder. So the inputs of this autoencoder had convolutional layers, because we arranged the data in grids. So we had in one axis the frequency of the events, and in the other the time. In the end, if we chop that and we put in a long stack, we have kind of a very long time series. In this case, the data comprised all the events for whole fleet for 1 year. So that was a lot of data. So it was a very long time series. And based on that, we simply gave that to the algorithm to learn how a causal structure could be learned from that, taking into account the limitations of the parameters. Did I solve your question? Okay, well, yeah. We can continue discussing about that then. Yeah, thank you.
Any other questions? All right. In that case, let's give one more round of applause. Thank you very much for everything.